And then we take the average by adding all of those up and dividing by n minus 1, okay? Or n, but n minus 1. For a set of numbers, we do this. Sound familiar? So it's like the average, okay, squared distance from the mean. Okay, so what we're going to do is we're going to take each data point, essentially, and we're going to break up the deviance from the mean into two parts. Part of it is due to the fact that the group is different from the mean, and then the other part is the individual difference from the group. Okay, so let's say if this is the mean right here, and someone is out here, okay, we are going to take, this is the total distance from the mean, okay? And what we might say is that maybe this point belongs to a group, and that group's mean is right here. And we're going to break up this total distance from the mean into the fact that the group is different from the mean. So this is, group is different. And then, and this part is that the individual is different from the group. Does that kind of work? So we're breaking up, so everybody's different. But we're going to, rather than just say this person is this different from me, we're going to break this distance up into, part of it is due to the fact that this person is in this group, and that group is different from the mean. And then, as an individual, that person is different from his or her own group. Okay. So, let me think of an example here. Okay, this might not be a good example, but I'm going to go with it anyway. Let's say we could assign some number to your political ideology. Okay, there's all sorts of flaws with this to begin with, but let's just say you're either assigned a 0 to 100. Okay, and if you're in the middle, you're at 50. And I recognize the flaws in this because politics can be is multidimensional. But let's just say there's only, let's say if you are very liberal, your score will be 0, okay? And if you're very conservative, your score will be 100, okay? That's as liberal as you can get would be 0, and as conservative as you can get would be 100. And if you're right in the middle, you would be 50, okay? So if we looked at Congress, you would have probably a bunch of people in the low section and a bunch of people section, okay? But if we looked at an individual senator, an individual congressman, or congresswoman, or congressperson, we could, let's say the average for the Republican Party, or the conservative group, was, let's say the average score for conservatives or Republicans was 80, and the average score for Democrats was 20, okay? When we look at an individual, maybe somebody has a score of 65, okay? We could say this person has a difference from the mean, which should be 50. That difference is partly due to the fact that this person is Republican and that group's average is 80. But then this person is maybe not as conservative as the rest of the group, and so an individual difference brings him back down to 65. Okay? And we can do that with every person. We can say, but this person, this person is like the super Republican or whatever, and this person scores 99. So they're even more extreme than the rest of the group or something. Yes?
So there's two differences then. There's one from the total mean, right? That's what you're saying?
Yeah, so this is the total mean right here, okay? So there's a whole bunch of data points, okay? Alright, and that the total mean is right here. And we're looking for each data point, we're going to say this is the distance from the grand mean, okay? And that's what will go in towards total variance, right? We're just looking at the difference from the mean. Okay? But we're going to break up this difference into two parts. One is is attributed to the group difference, and then the other part is attributed just to individual differences.
Okay, so if we're going to apply it to the example, I don't know if you're going to do that.
Yeah, so I'm going to do it to our thing here. So, okay, is that okay? All right, so we can look at this lamb right here. Okay, this lamb gained 6 pounds. The average weight gain of all lambs was 13 pounds. Okay. And so this lamb gained 7 pounds less than the average. Then I will say grand mean. Well, we can say, well, part of it is because this lamb was assigned to diet 3, and diet 3 on average gained a pound less than the grand mean. Okay, so part of this 7-pound difference is because he gained, he was in diet 3. Okay, so this will be the group difference, or difference because of the group. And then as an individual lamb, this lamb just gained less than the rest in his group. This will be the individual difference. Okay. Is that all right? This lamb over here, also in diet 3, gained 17 pounds, which is 4 pounds more than average. 4 pounds more than the total average, grand mean. Okay. And we will say, well, this lamb was assigned to diet 3, so we would expect that the lamb would actually be losing weight, because the overall effect of diet 3 was a 1-pound loss. But this lamb overcame even that disadvantage and gained 5 pounds more as an individual. Okay, so so we still have the group difference, which is the same, but then as an individual, gain 5 pounds more than the group average. Okay, so we're breaking up the basically total distance from the mean into 2 parts. Can we see what we're doing here? Okay, this is why we're calling it analysis of variances, because we're breaking up the total variance. Okay? Okay, so essentially we're just going to focus on the difference from the mean, and we're just going to ignore the taking the average, the n minus 1. Okay, so we're dealing with what we call sum of squares. Sum of squares, and it's basically the squared distances. Okay, so it's really sum of squared distances. And so we break up into what we call sources. And we have between the groups and within the groups. And within the group, this is basically the individual difference. I'm going to create a column called data, but we'll come back to that. So the total sum of squares is what we would get if we took each point y, subtracted off the grand mean, in this case y double bar, and we squared it. And we did that for all points. To indicate that we're doing it for all points, I end up doing a double sum. Sum is for all points within a group and for all groups. Okay, but essentially, the double sum, in effect, in this case, means for all points. The sum of squares, the individual difference, if I were to go through and I were to try to figure out the individual difference from the group mean for all of these points, what I would be doing is I would be taking each point, subtracting off the group mean y bar, and squaring that. And I would do that for all points within a group, and then I would do it for all groups. Okay? All points in a group for all groups. Alright, and then for the sum of squares between the groups, I'm doing the different group difference there. That is the group mean, y bar, and how different is it from the grand mean, y double bar. Okay. And I'm going to take that difference and I'm going to square it. And how many times am I going to do that? Well, for all the points in diet 3, they all have the same group difference, right? Okay? So I'm going to do this 1, 2, 3, 4 times. 4 times. And it's basically all the points within a group have the same group difference. So I'm going to take that difference, the group mean, minus the grand mean, and I'm going to square it, and I'm going to multiply it by how many are in the group, and I do this for all groups. Yes?
Where you have source in between groups and within groups, do those correspond with the formulas?
Yes.
To the right?
So the between groups, this is sum of squares between the groups, and this is sum of squares within the groups.
What about source?
Oh, source is the column heading.
Okay.
Okay. So I'm breaking up the total distance into 2 parts. One is the individual or just differences within the group, and part of it is due to the fact that their group was different from the grand mean. Does that seem reasonable? Okay. This within group can become rather tedious to calculate because we would have to do it for all individual points. So we can use the summary statistic, okay? And so if we recall the formula for what standard deviation S is, it is y minus y bar squared over n minus 1. Okay. This is the formula for the standard deviation. Okay. Well, what do we notice? This part is the same as this part right here. And so I can square both sides, and I would get s squared is equal to the sum of y minus y bar squared over n minus 1, and I can multiply both sides by n minus 1. Okay. And so this part right here can be replaced with this part right there, because that's what we have. Okay, so I'm going to just rewrite everything in a little bit neater form. A little bit. Can I erase this? No? Not yet. Oh, wait. Okay. I'm going. So if I do sum of squares between the groups, and within the groups, so we have degrees of freedom. So the degrees of freedom exists here also. The total degrees of freedom is the number of points minus 1. Degrees of freedom between the groups is the number of groups minus 1. And within the group's degrees of freedom is plus this has to add up to this. And so it ends up being number of points minus number of groups. The book abbreviates number of groups as the letter I. I feel like some more letters than we need. And the sum of squares total, it's what I had before is still valid, but it can also be quickly found as sum of squares between plus the sum of squares within. So you can add those two numbers to get sum of squares total. Alright, so shall we find sum of squares? Okay, so sum of squares between the groups. I'm going to take each group difference. So that first group has a mean of 11, and the grand mean is 13. So every point there, its group mean is too different from the grand mean, and there were 3 points. So I'm going to multiply that by 3. And I'm going to do the same for all of the other groups. And as for the within group, I would do 4.359 squared times, I'm doing this n minus 1, plus 5 minus 1 times 4.950 squared, and 4 minus 1 times 4.967 squared. And if I do that, I get 210. Maybe a little bit different because of rounding issues. What would how many degrees of freedom do I have for between groups?
2.
2. I've got 3 groups minus 1, so I have 2 degrees of freedom. How many degrees of freedom do I have within the groups? I have 12 points total, minus 3 groups, 9 degrees of freedom. And the total degrees of freedom would be 12 points minus 1, 11. If we wanted to find total sum of squares, we would just do 210 plus 36, 246. So I have sum of squares. I'm going to just replace them with the numbers now. 36 and 210. And so what we want to do is we want to compare whether the difference due to the fact that the groups are different, is that large or small compared to individual differences? If the difference between the groups is large compared to individual differences, then we would have evidence that the groups are different. If the group differences are small compared to individual differences, then we would not have evidence that the groups are very different. Okay? Well, these numbers will always seem, if we look at the sum of squares directly, this will always appear small because we have a whole bunch of individual points. Okay? So we look at something what we call mean squares, or MS. Okay? And all this is the sum of squares divided by degrees of freedom. Okay? It's the same for both rows. So in this case, I would do 36 over 2, and I would get 18. And over here, I would do 210 divided by 9, and I would get 23.33. So this is what we have. And we're going to create a ratio between the mean squares between the groups and the mean squares within the group. And this is called our F ratio. So it's mean squares between divided by mean squares within. So our F ratio in our case is 18 over 23.33, and I get an F ratio of point something. I actually don't have a calculator today. 0.77? So that is our F ratio, and that is our F statistic, okay? Or our test statistic. This is a test statistic that we use, and if we wanted to get a p-value, we would look this up in our reference tables.
Which one?
Which one? Okay, so I did not print out the F table as part of your packet of reference tables. I figured if you know how to use the chi-squared and all of the other tables, you can use the F table easily. Okay? And the reason why I didn't print it out is that the F table is many, many pages long. Okay? There's one page in the F table for each what we call numerator degrees of freedom. Okay? And so our F ratio has a numerator, 18, and 18 has 2 degrees of freedom associated with it. And denominator, 23.33, and it has 9 degrees of freedom associated with it. Okay. And so to use the F table, you would need, well, we have the numerator degrees of freedom, which is 2, and denominator df, which would be 9, okay? And so you would flip to the back of your book and you would see several pages of the F table, and you would go to the page that says numerator degrees of freedom 2, and then in that table you would find denominator degrees of freedom 9. And then you would use the table accordingly. one, and if you have your book, I believe it's page 629 in that case. And so, in that case, the first value that shows up is tail probability is 0.2 and has a test statistic of, or a critical value of 1.93. And so we see our test statistic of 0.77 is closer to 0 than 1.93. So our conclusion would be that our tail area is greater than 0.20. Okay. When you do the F ratio, you're always assuming a non-directional test. So our p-value would be greater than 0.20. We would not, no need to double the values in the F table. They're already set up as such. Yes.
So were those just in the table? I don't have it.
So yeah, so in your table you would go to page 629, which corresponds to numerator degrees of freedom 2, and then you would find the row for degrees of freedom equal to 9, denominator degrees of freedom equal to 9. Okay. And your first value in that table with 9df would be 1.93 and then 3.01. And this corresponds to a tail probability of 20% and 10%. And so we would say that 0.77 falls over here, so that must mean our tail, or our p-value, must be greater than 20%. Is that okay? Alright, so let's try, let's have you guys try out an example.
So Professor, when we have this on a quiz or exam, you'll just give us the corresponding page?
I probably won't even bother having you look it up in the table. I'll just say, what is the test statistic that you would look up? Or something. I don't know. If you can use the chi-square table and the t-table, then I don't see a reason why you wouldn't be able to use the f-table. Okay, so I don't think we're losing educational value by me not testing you this concept here. Okay, let's find, we can just pull an example here. No. Let's see. Okay, you know what? Let me boot up the computer here. Let me talk about what you might have to do, or what you'll have to do this week for the lab. Okay. So this is your lab assignment this week. Just or I don't know what you call this, reading assignment. You can skim through the article. It's not super interesting, but it used one way ANOVA, and it was simple enough. It was hard to find a good article that used one-way ANOVA. Like I said, one-way ANOVA is the simplest form of ANOVA, and so most or many experiments today use something a little more complicated. Okay, all right. So this is the article is age-related differences and factors associated with smoking initiation. So basically, they surveyed a whole bunch of people, and they said, they surveyed a bunch of people who were current smokers or former smokers. Okay, and they said, when did you start smoking? And they said, I started smoking when I was this old. Okay, and they asked them. Then they also looked at a bunch of demographic information and asked them about their smoking habits. So they said, we looked at their sex, their race, and et cetera, et cetera, et cetera. And this is, these are the results. Can you guys read that? Too small? Okay, so we looked at a total of 1,447 people, and the average of everybody is, when we asked them the question, when did you start smoking, the average age of all 1,400 something people was 17 and a half years, with a standard deviation of 3.8 years. Okay. And then we looked at the men, and we said, when did you start smoking? The average age that the men started smoking was 16.8 years, and the average age that the women started smoking was 18.3 years. Okay. And you could do an ANOVA, but you could also just do a t-test. So because there's only two groups, you can do a t-test. And if you did a t-test to see, is it possible that the means of the men and means of women were the same, you would get a p-value of less than 0.001. Okay? So every time you see a p-value, that is a test being carried out. Okay. Then we looked at ethnicity. Okay, and there were, we split them into three groups: non-Hispanic, white, Hispanic, African American. And we said, when did you start smoking? And the average age for non-Hispanic white was 17.3 years, average age for Hispanic was 17.5 years, and the average age for the African American group was 18.4 years. And so in this case, you would have to do one-way ANOVA because you have three groups, and if you did one-way ANOVA, you would end up getting a p-value in the vicinity of 0.001. Okay, is that all right? And they did that for different things, such as educational attainment, whether your parents smoked, et cetera, et cetera, et cetera. Okay. So, but again, the weakness with ANOVA is that even, so with ethnicity, we don't know which group is the group that's different. Okay. Now, looking at the numbers, it might appear that the African American group is larger, 18.4, meaning they started smoking later than the other groups. But that's also hard to say. That might also be due in part because that group is smaller compared to the other group. So with ANOVA, you can't say this is the group that's different. All you can say is that the groups are not the same. And you would have to do individual tests to see which one is different, but then that's also difficult. And of course, you know, when you have just two groups, which group is the different one? You know, they're different from each other. Is, you know, can you call one the baseline of the other? You know, it's hard to say. Okay. So anyway, they looked at demographic information, and then they also looked at habits. Okay. You know, was there a difference between, you know, if you use menthol, was there a difference in when you started smoking? Maybe, maybe not, okay? Here it shows a p-value 10%, so probably not, okay? But if, you know, if you smoke 39 years or more, you're more likely to have started smoking at a younger age or something, okay? Then they looked at a whole wide range of things, okay? So,
I have a question.
yes?
So can you explain what the p-value means regarding, let's say, one of the groups?
Okay. So let's look at, let's go back. Okay, so let's look at this ethnicity thing, okay? So we have three groups. The null hypothesis is what? Is that the group means are all the same. Or is that it doesn't matter which ethnicity you are categorized as. When you started smoking, or the average age of started smoking is just 17.5 years. And yeah, everybody's different, so some people started smoking earlier, some started smoking later, but that's just the overall average. And the group doesn't matter, that's what the null hypothesis says. So the null hypothesis says that if we looked at the populations, they would all have the same mean age of smoking, mean age that they started smoking. The alternative hypothesis says, actually, the groups have a different mean age where they started smoking. That would be the alternative hypothesis. So we get a p-value of 0.001. So that means if I assume that the null hypothesis were true, if the age that someone started smoking has nothing to do with their ethnicity, what is the probability that a random sample of 1,400 people would give me mean values that are just different from each other? Okay. What is the probability that I would end up happening to get a mean of 18.4 here, a mean of 17.5, and a mean of 17.3, just from random chance, if ethnicity has nothing to do with when someone started smoking? The probability of something like that happening from random chance is 0.001. So that would give us reason to believe, you know, the results I see here probably didn't happen from random chance alone. Okay? It's possible, but it's this p-value indicates that it's very unlikely that random data is going to produce, you know, means that are just this different from each other. So therefore, I would probably conclude that ethnicity does play a factor in the age that someone started smoking.
Well, it does play a factor. I would think the opposite.
That it doesn't, or?
Right, that it doesn't. But if it was a high p-value, then it makes a difference.
So yeah, no. So here the p-value is small, so it's indicating that
They're all equal.
That we are unlikely to see data like this from random chance alone. And therefore we have reason to believe that ethnicity plays a factor in when someone starts smoking. So again, when your p-value is small, you reject the null hypothesis. Okay? So the null hypothesis says that ethnicity doesn't play a factor, everybody's the same.
Right.
The alternative is that ethnicity plays a factor, the different groups are different. P-value is small, so we reject the null, come to the conclusion that ethnicity plays a factor. Is that okay?
Yeah.
Alright, so let's see if we can verify this p-value based on the data that we have.